Hi there, AP Calc students. Time to be in another new unit. This is going to be a unit now on applications of derivatives. So we won't really be learning any new rules of differentiation or anything like that, mainly how to apply them in various settings. So today's lesson is called extreme values of functions. You'll recall a lot of these ideas from even pre-calculus, I believe. First of all, let's take a look at some things you might be familiar with. If this were a particular function, we could label the extrema of a graph. Extrema refers to things like maximums and minimums. And of course, we remember that we have things like absolute minimums, that's the very lowest points of the graph. And then we have some relative maximums and relative minimums, which are kind of high points and kind of low points. You should be aware that in our calculus textbook, they use a little bit different terminology. Instead of the word relative, they would perhaps use the word local. Means the same thing, just a different terminology. And instead of using the word absolute minimum, they will use this word global minimum. So just a little bit of a change in terminology, otherwise I think you'll be able to figure that stuff out fairly well. Now, this is a chart that's pretty much in your textbook, I think, but I just thought it would be helpful to get this in your notes and explain this a little bit. The extrema at endpoints, especially endpoints. And so this is a familiar graph, y equals x squared, a parabola, but we're going to look at it in various domains. Now, keep in mind that when we talk about these domains, that what we mean by a brackety thing like this is a filled-in circle. And anytime you see a more of a traditional parenthesis like this, it means an open circle. So a closed interval would be something like this, meaning the endpoints count. An open interval, as we see here and in partially some of these other ones, that means that the endpoints do not count. Anyway, let's say we had our whole domain from negative infinity to infinity. There's no absolute max because the graph just keeps going higher and higher in both directions, of course. There is an absolute minimum, however, at x equals 0. That's the lowest point, the vertex of the graph. Now, the next part is where it starts to get a little bit interesting. What this means now when we have this domain is that at 0 there's actually a filled-in circle like this, and also at 2 there's a filled-in circle. So I'll try to make my best filled-in circle like that. So really we're looking at this portion of the graph here, just like that. Now in this case it does have an absolute maximum, which is right here, and it does have an absolute minimum. The endpoints are defined so they can count as those extrema like that. Now let's take a look at the next one though. Here this is a little bit different. Now at 0, since we have that parenthesis like that, we have an open circle. Still at 2 we have a filled-in circle like this for an endpoint. So now my graph looks something like that. Notice we still have our absolute max because of the filled-in circle, but, and this is something that confuses students sometimes, there is no absolute minimum. No absolute minimum. And you might say, well, why not? It looks like this would be the lowest point of the graph right here. But keep in mind that x, in this case, can never equal 0, and even an infinitesimally small x value that's just a little bit larger than 0, we can always give you one that's a little bit less, and the y values would keep going down. So clearly the open circle would signify that there is no absolute minimum here. And then, as you might guess what might happen on the last interval here, open circle at 0, open circle at 2, same type of graph basically, but there are no absolute extrema here because of those open circles. So make sure to get those in your notes. That might not make total sense to you right now, but we'll be referring back to that later. Now here's our extreme value theorem. This is fairly important here. So this says that if f is continuous on a closed interval, again those endpoints have to count then f has both a maximum value and a minimum value on that particular interval. So if I could do some examples here, if I just have something that looks like this, again if it's a closed interval like that, with the endpoints counting, then certainly there's going to be a maximum and a minimum value on that interval. And it may very well be at the endpoints, as it looks like it is in this case. If I do another example here that maybe looks like this, well, here's my traditional parabola. Clearly, this has a minimum value on this interval, and even my maximum value there too. So that's the extreme value theorem. And a key word there is closed interval right here. And it's going to have a maximum and a minimum value someplace on that interval. Now, what about local extreme values? Local, of course, is kind of like relative that we have learned about before in pre-calculus. So let's take a look at this theorem. So this says that if a function has a local maximum or local minimum value at an interior point, so not an endpoint, but an interior point, that means, and if it's basically a continuous function, if the derivative exists at c, that means that that's where the derivative is going to be 0. And we've kind of alluded to this a little bit last chapter. When we saw a maximum or a minimum point, that's where the derivative was 0. So just for instance here, if I draw a quick little graph like this, and let's just say that that just keeps going on and on like that. Well, I know that this could be considered a local maximum, and this could be considered a local minimum right there. When I look at the derivative of that, the derivative is going to be 0, as this theorem says. Why? Well, remember our derivative, as we think back, is really just another name for our slope. And we'll have positive slope, positive slope, positive slope, negative slope. Right here at this relative maximum or local maximum, that's where that slope is going to be 0. Same thing down here, negative slope, slope of 0, positive, positive, and so on like that. So that means in the interior, if there's a local maximum or local minimum, then that derivative is going to be 0 in there someplace. All right, here's kind of an important terminology that we'll use quite a bit of, critical point. And again, I believe we did define this in pre-calculus as well. A point on the interior of the domain, so again, it has to be an interior point that we're talking about. And a critical point occurs there if the derivative is equal to 0 or the derivative does not exist. So if we have those two criteria, it's called a critical point. So of course, when we have the derivative equal to 0, that's where you have your maximums, your minimums. Where we have the derivative does not exist, remember those are places like corners and cusps, things like that, vertical tangents. Those are places where the derivative does not exist, if you remember from last chapter. So in summary here, this is kind of a helpful sentence, I think. Extreme values occur only at critical points, meaning a derivative equal to 0 or some place where it doesn't exist, or endpoints. Those are the only places where those extreme values will exist. All right, find and classify the extreme values and where they occur. So I'm just going to draw some goofy graphs here. Once I find a nice color to use, I guess I'll go back to that blue. So what if I had something that looked like this? That particular function like that. Where would the extreme values be? Well, I meant this to be filled in here. So certainly right here, we could call that a minimum, and that looks like if this is all the function is, this would be like a global minimum right there, right? What about this and this? Well, again, because they are open circles, there's not going to be any kind of extreme, any kind of maximum or minimum that occurs there. We could call this point right here a relative min, like that. All right. There'll be some problems in your book that we'll be working on like this as well. But mainly just looking at the graph, basing it on our definitions and our theorems that we've looked at so far, trying to figure out where those extreme values are. It's pretty much common sense. The only thing that might goof you up a little bit are these open and closed circles. All right, here's a couple examples here that we'll try to get through fairly quickly. Use analytic methods, that means algebra basically, to find the extreme values of the function on the interval and where they occur. So here's our particular function right here, g of x equals e to the negative x, and we want to look at it between -1 and 1. First of all, we are going to draw a little graph here, just so you get a feel for what this function looks like. And it does look something like this. I'm going to get a different color here. When x is -1, it's going to be way up here someplace. And when x is +1, it's going to be down right about here, let's say. All right, so we can tell by looking at this where the extreme value is going to be. Well, it looks like they're going to be at the endpoints, doesn't it? It looks like this is going to be a maximum and this is going to be a minimum. The endpoints are defined. There's no other place in the middle where there's a critical point or anything. So that's where the extreme are going to be. Let's see if we could sort of verify this algebraically, though. All right, so again, we're looking for what's the derivative of this. And as remember, the derivative of anything with e is the same thing, but then we have to multiply it by the derivative of the exponents. That's going to be -1. So this would actually be negative e to the negative x, and another way to write that even is -1 over e to the x. Now if we look at this, this is never going to be 0. Why not? Well, the denominator can never be 0, so the actual value of the function can never be equal to 0 either. So that leads us to believe that there would be no critical point here in this derivative. Again, what's a critical point? Critical point is any place the derivative equals 0. That means maximum or minimum. Or it might be some place where there can be no derivative, like a corner or a cusp. So, again, the only places where the extreme values can occur are at the endpoints, and so those places would be the g of -1, and just analytically then I could write it like this, just put -1 in place of x, so that's e to the 1, or just plain e. We know that that's equal to about 2.718, so that's your left endpoint there. And then the g of 1, just putting 1 in place of x, that'll be e to the -1, or just plain 1 over e. Not quite sure what that looks like. So my maximum value would be represented by this, and my minimum value would be represented here. All right, so we used a little bit of algebra with a little help from our graph there to figure out some extreme values for that. All right, let's see what we can do here. So here I have another function. Let's quickly look and see what the graph looks like of it. X to the 3/5 power. So if I graph that quickly, it's going to look something like this, I think. Notice at -2, it's going to be an open circle, I believe, right? And at +3, it's going to be filled in. Again, we can kind of tell from looking at this graph that same situation is going to be here. We're not going to have anything going on in the interior. It's always going to be in the exterior. And so, again, since I'm running short of time, I'm going to quickly say that my maximum value is going to be there at 3. So my maximum value is 3. If I put 3 to the 3/5, whatever that ends up to be, that's going to be my y value. And what about my minimum value? Is it going to be the left endpoint? No, because of that open circle. So in this case, actually, then, that there is no minimum value. no extreme value that's a minimum in this case. All right, lots of stuff here. Thanks for watching, everybody. We'll talk about this in class.